I know I'm going to the other one. I will just put this on here.
Okay, could you please take your seats? So that we can resume the seminar for this second part of the morning. We'll hear now the third presentation of the experimental results by Reinhard Stock, which is entitled Hadron Signals from the Little Bang. Reinhard?
So next I will talk about bulk hadronic production and what we learned from it as far as the phase transition is concerned. With these high-speed talks, I give you my conclusions at the beginning, then I can safely come back to them at the end. So the menu chart of my presentation, which covers results from 4 experiments, is more or less analogous to what we learned from Uli in his introductory talk. The punchline will be the following. First, we want to know something about the primordial system right after interpenetration of the 2 head-on colliding nuclei, and you want to make an estimate of the energy density. And I will show from calorimetry and from Bjorkane's estimate that this energy density is of the order of 3 GeV per cubic Fermi, from which rather simple measurement and interpretation, you know right away that one is on the right path in looking into deconfinement, because QCD says that above between 1 and 2 GeV per cubic Fermi, there is expectation of deconfinement. Next thing is, if you have initially a deconfined state, of course it must expand and rehadronize, as it does in the Big Bang. So what can we say about that instant of time when the system undergoes a phase change between a partonic phase and a hadronic phase? And I will try to tell you that the system of hadronic production rates from the very abundantly produced pion to the very rarely produced hyperons, about which a special treatment will be given in Emanuele Quercik's next talk, plus an interpretation by more or less a revitalization of Hagedorn's model, leads to an estimate of the critical energy density of this phase transition, and the temperature of about 175 MeV, epsilon the density 1.1 plus minus something, again quite in confirmation of what we have recently heard from lattice QCD. So essentially these experiments demonstrate the reality of these lattice QCD estimates. Then where is all the explosive energy going to that we have created in compressing this highly excited and compressed fireball? It goes into an explosive expansion, and the final traces of these expansion processes I will show you in terms of spectra and correlations prevailing in the very end, the last snapshot of the dynamics before the system disintegrates. And then another question which is also of high relevance to astrophysicists, building a model of proton-neutron helium formation in Big Bang from the transition partons to hadrons. They would very earnestly want to know whether the phase transition is or is not first order. So can we say something about the nature of this phase transition? And we have first indications of this. So now I put this over here that you can watch my progress, and I can also watch it myself. And the time. Before, however, I go to showing you the data, I have to show one transparency in which this community of relativistic heavy ions says thank you to the CERN accelerator divisions. Because it was by no means a single-shot adventure to get lead produced in the CERN accelerators. All you colleagues here know the details, but maybe the guests do not. So it was amounting to building a special injector, then a special LINAC, And that was devoted to the lead acceleration program. And then we go through the well-established instrumentarium of the PS booster, the PS and the SPS, but also serious alterations and improvements had to be accomplished, for example, in the vicinity of the PS. These machines proved versatile enough to turn away from accelerating electrons and protons now to accelerate fully stripped lead in this 82 plus ionic state. And this is what we are talking about in the experiments. Of course, the total of 33 TeV beam energy creates events which are, experimentally speaking, formidable. And you can see here a picture of NA49, a multi-tracking TPC detector, shows about 1,200 created charged particles. Altogether, we have about 2,500 created charged particles, and it is a formidable experimental task, of course, to unravel this multiplicity. So I'm coming to my first item on the agenda, namely, can we say something about the primordial energy density? Louis also referred to the scale of energy density in some primordial state when he pointed out the point where the J-psi signal finally settles into disappearing. And he said that is at about 2.6 GeV per cubic Fermi. Okay, if you do calorimetry of the primordial state by measuring the total transverse energy spectrum in rapidity space, then you get this kind of Gaussian-shaped curve, which shows you that indeed at mid-rapidity you have the maximum energy density concentration. So you are really forming a fused system of matter of fireball-like qualities in the center of mass. And then if you apply to the combination of this peak value the so-called Bjorken estimate for the volume from which this transverse energy is radiated, you get the estimate 3 GeV per cubic Fermi from experiments WA98 and NA49. So that was topic number one, which was an easy one. So we are underway, and we knew this already 4 years ago, that we would be underway in terms of detecting and outlining the phase transition. Because these calorimetric data are rather simple to get. You do not deal with all the differentiation of the individual thousands of tracks. Now we come to the second part, looking at these thousands of tracks. The task now is to measure the systematics of hadron production from pi via k to lambda, omega, psi, etc., etc. And you do this as a function of collision centrality, from peripheral collisions where the number of participating nucleons is small, to head-on where you have about 400 because you bombard 208 mass nuclei. And you see here, for example, the total kaon yield in relation to the pion yield. And you see the phenomenon which one usually calls strangeness enhancement by about a factor of 2. From the proton-proton level to the central lead level, there is a good factor of 2 of enhancement of strangeness production. Most of the strangeness that's produced goes into kaons, actually. And we will see other aspects of strangeness production later on. Just to compare to data from a different experiment, you see in the two plots here of NA52, similarly as a number of participant protons or centrality, the kaon production ratio increases smoothly and settles near the central collisions. NA52 is shown also as an example that you do not only measure kaons, K- production in rapidity space, but antiprotons, and that particular experiment goes on to measure antideutrons and obtain an estimate for anti-helium-3 production. If we take the sum total of all these systematically measured production rates and their ratios, and plot them in a plot which I will show in 3 different variations, this is the first one, versus the prediction of a statistical phase space model, then we see that the yield here is, of course, the mostly produced particle is a pion. Here is the experimental data scale from, in this case, from NA49. This is a prediction of a model, which I will describe in a moment. Pions, most abundant, and protons, kaons, down to the psi's, lambda to anti-lambda ratio. And you see that with a statistical phase space model, which is my way of saying a Hagedorn-like model, you can interpolate with actually two parameters, essentially, all these different hadronic production levels at one glance. So the information contained in this is not 16-fold as the number of entry points might suggest, but is one and the same thing that is reflected here, and this thing is the energy density prevailing at the point where these hadrons are born. They are born in the parton to hadron phase transition, and therefore the temperature that is estimated from the statistical phase space model analysis, this one by Beccattini in Florence, shows temperature estimate of 176 plus minus 12 or 10 MeV. This is now our estimate for the parton to hadron phase transition. And in this particular model, the energy density here is about 1 GeV per cubic Fermi, and you recall that this was also somehow foretold by QCD lattice. Just because we are in this room, I cannot resist quoting Rolf Hagedorn from a 71 lecture, which probably not from this, but in the other room. Hagedorn has already written down the key recipe that I'm using here, namely the particles whose equilibrium is used and described here are born into this pre-established equilibration state, which is nothing else than the quantum mechanical probability distribution of all possible particles in the final state. So this birth is by a simultaneous quantum mechanical transition matrix from partons to hadrons, of which these statistical models, let's say, are a quasi-classical approximation. And I found recent enlightenment in an article by John Ellis and the late Klaus Geiger concerning this topic. The same general idea is also shown with a different approach by my neighbor on my left hand, Johanna Stachel and Peter Braun-Munzinger, a different way of showing the data. The model was already shown. The data are the inputs from all experiments, including also WA97. And the fits are the same thermal model as one tells. And you see here the temperature is 170 MeV, quite in agreement. Last point is Kleiman's recent fit. Now again, this is NA49 data. You see the same feature again. Essentially, all the systematics of relative yields is represented by one simple set of parameters. It's 175 MeV, 1 GeV per cubic Fermi, and that is our estimate of the energy density of the phase transition from partons to hadrons. Point number 3 on my menu chart, what is remaining of the initial explosive energies that were accumulated in the highly excited fireball, which is now from the primordial energy density of about 3 GeV per cubic Fermi, has just gone under my hands through the phase transition. Now it's at 1.1 GeV per cubic Fermi and 175 MeV. Now it's still elastically interacting because the hadrons at this stage are closely and densely packed, which accounts for Johanna Stachel's in medium effects on the vector masses, vector meson masses, and widths. So it must keep decaying until it really cools off from strong interaction altogether. And let's try with 2 arguments to catch a final snapshot of this eventual explosive state of expansion. It's like Big Bang dynamics in a way, because nowadays all these interesting phase transitions in the universe are long over, and we are witnessing some kind of ordered radial expansion, and maybe we recover the same impression from these data. Start with data already Johanna showed, but with a completely different aim. Pi 0 from WA98, charged pions from NA45. You see beautiful transverse mass spectrum extending over 7 orders of magnitude, giving an impression of how precise one can measure innocent pions in this mess of 2,500 created particles which are emitted at once. This is central collisions late. See very nicely agreeing data. I just show this now because another measure of the conditions during expansion is now derived from the spectral slope of such MT or PT distributions. Remember Maxwell-Boltzmann, the slope of the momentum distribution is controlled by the inverse temperature, and so we will look at this. Maybe we learn something about the expansion. Important data from NA44 on spectral slopes on the same MT scale for K- and K+ production, and they deduce effective temperature parameters, which are around 250 MeV. Let's let's not get surprised. Now we are extracting thermal Maxwell-Boltzmann temperatures of 250 MeV, so don't get confused that before I said the phase transition is at 175 or 180. So of course the hadrons cannot thermally intrinsically be hotter than 180. So this excess in temperature over 180 signifies something else, and I will show you in a moment what it signifies. If you also do the general systematics of this topic, you come to a plot which was first shown by Nushu from Berkeley, combining NA44, NA49, and WA97 data. All these spectral slopes for different hadronic species, with the notable exception of the omega, on which I'm sure Emanuele Quercik will comment, of course there's always an excursion from some rule, but all the others follow a monotonous trend. The spectral slopes, which one has up to now, oftentimes called temperatures, but they are something else, as you shall see in a moment, go from about 150 for the pions up to about 400 for the deuteron emission. So what is this inverse slope or the spectral temperature really trying to tell us? And I will show you now that it is trying to tell us that the system has two forms of energy while it is expanding. One is thermal energy, which is more or less falling down from the energy density of hadronization to some very low value. And the other one is radial ordered collective flow energy. So the total that you see in the spectra is a kind of relativistic superposition of two modes. One, a radially symmetric, cylinder symmetric expansion of the system, and the other one, the superimposed chaotic thermal field that prevail during expansion while the system cools. And the addition of these two forms, radial escape energy in ordered collective flow and internal thermal energy, causes these spectra to have apparent slope values which are far beyond the temperature itself, because there is an additional ingredient at the end of the flow velocity. Of this condition, one can also get another snapshot by looking at Bose-Einstein correlations in the final state. This is a two-pion correlation function in Bose-Einstein correlation analysis. You also know this under the name Hanbury-Brown-Twiss effect. You see that momentum space is here disentangled by a transverse difference in momentum, by a longitudinal difference in momentum, and by a time-like difference in momentum of the considered pion pair. And whenever these differences in momenta go to zero, you have a maximum in production, because now you have identical pions, two of them, finding out that they are bosons, so they are all at a sudden twice as probable in this state as if they were not seeing Bose statistics. And from this effect, which already Hanbury-Brown and Twiss used to analyze the geometry of the emitting sources, we are now analyzing not just the geometry, but also the time dependence of this geometry from hadronization to freeze out. And in this analysis, you can pick up the collective velocities. Now, I will not be able to go into theory, but repeat what Uli Heinz showed, a transparency of that data that lead us to speculate about a collective radial expansion field. If this was not present, then the display of these radial parameters versus the transverse mass of the observed particle pair would be a straight line, but you see there's a very distinct falling trend, and from a theoretical representation of this fall, one can deduce the final radial expansion temperature. So one combines now these two sources of information, what we learn from the spectral slopes and what we learn from Bose-Einstein correlation. And this leads to a complicated plot which excludes parameters in a space of freeze-out temperature for eventual decoupling from strong interaction and radial collective velocity beta. And if you combine all the information provided by the Bose-Einstein correlation, which leads to this corridor in this plane of allowed values which are extracted and compatible with the data. This is from the deuteron spectrum of NA49. This is from negative hadrons. And there is a correction to this analysis recently pointed out to pions from WA98, which lets these lines not level off here, but continue in this red fashion. And if you look for the overlap of all these three independent parametrizations of the expansion features, which one calls radial flow, in terms of final decoupling temperature and radial escape velocity or explosive velocity, you come to an allowed overall region, which is this green hatched area, which tells you that the eventual velocity of the decaying system is about 0.6 of light velocity. So this is a highly explosive decomposition in the end. It shows a radially ordered final picture of the dynamics, which is of explosive nature. So that much we have learned about the overall dynamics. There's also some kind of rather interesting feature that one learns in these collisions, namely one learns something about the volume of the source as it freezes out. And now here you see an estimate of the volume of the source, which is coming from 2 pi times the transverse radial parameter of the HBT analysis squared times the longitudinal radius. So this is a cylindrical volume element. And you can see here from peripheral collisions in lead-lead up to more and more central, this volume shoots up. And it shoots up in a yet not completely understood non-trivial way, because you would expect that some kind of smooth geometrical condition is the overriding thing. But there is also in these measured freeze-out sizes an effect of dynamics. You see these data of NA49 completely agree with this trend. It's basically the same data. This volume shoots up in the end for very peripheral, very central lead-lead. Then it has some kind of shoulder, and then it goes into zero. This is something which is just hot off the press and calls for more analysis. So that was the second last point. And now very briefly about the last point. Now, can we learn something? We have learned now where the phase transition occurs, at which energy it occurs. We see how the system leaves the site from this transition and finally is in an explosive radially expansion state. That is the last snapshot of this dynamics that we have. Can we say something about the nature of this phase transformation? Is it first order, second order, third order, no order? What is it? And one idea would be that phase transitions, as you know, are very often associated with critical fluctuations, pre-critical and critical fluctuations. At the instant of the phase transition, there is a divergence of the matrix elements which control either momentum transfer or any other dynamical variable which gets unbounded for a certain moment, and that makes the outcome, be it hadron number, temperature, composition, fluctuate in large-scale collective fluctuations. It's like in boiling water. The water is 100 centigrades and is ready to go. No, but the bubble is forming just where you have a seedling. This is once here, once here, once here, once here. So there is a large fluctuation of the actual phase transition site when you have a first order phase transition with a very large jump of latent heat. So can we see fluctuations? And I show you just one analysis is NA49. Actually, this is why we built the spectrometer with 1,200 hadrons per event analyzed. Because with these 1,200 hadrons, you can analyze each hadron, each event individually. You have about 1,000 pions in there. You have about 60 kaons in there. So for each event now, you can get the K to pi ratio and look at its fluctuation from one central collision event to the other. This histogram shows the result. Let's make it short. There is no sign of any critical fluctuation. The width of this distribution, which is in red dots, is entirely exhausted by a Monte Carlo simulation of the instrumental conditions under which we witness these fluctuations. Chief ingredients is the experimental resolution and the finite number fluctuation, which is very trivial. If you have 60 kaons per event, your counting number estimate fluctuates by 16%, because that's the statistics for this number of events. So there is no critical fluctuation in the data. Let's say theory is still in due action about the interpretation. So there are no significant large-scale fluctuations in these phase transitions. Whether or not this really has a consequence that we conclude the phase transition is not second order, not first order, I would for the moment leave somewhat open. If it is not really strong first order, we are in good company with lattice QCD, which is somewhat undecided about the nature of the phase transition as of yet. And in lattice QCD, there are indications that it might be second order. So these data want to see more action. So conclusion is, as shown there, we have seen the primordial energy density, we have seen the point of the transition, we have seen that the fireball decomposes in an orderly explosive mode, which disrupts the system as fast as possible, leaving frozen in it the previous stages in its hadronic composition, and that the phase transition seems not to be manifestly leading to large-scale fluctuations of the final outcome. Thank you.
Thank you, Reinhard, for bringing us through all the phases of these collisions and expansions. Any question? To complete the scenario? No? Yes?
Has anybody looked at the pi 0 to pi plus or minus fluctuations, which, as you know, have been proposed as a possible signature or something?
Yes. The answer is WA98. Hans Gutbrot is already affirmatively nodding. Has looked at this pi 0 to charged particles, and within the experimental exclusion limits, there was no such fluctuation as would be expected from decaying disorderly condensated states. But of course, that has its experimental limitations in the statement. No? At least if the whole interaction volume would be almost one gigantic disordered chiral condensate, then they would have seen it. So let's put it this way. Maybe Hans want to comment a little bit more in an educated manner.
Two people are hesitating. Who should comment? Do you want to comment?
It's correct what he said. You just can put it up front. There was no large gases.
Thank you. Other? Yes?
Yeah, I didn't quite understand what is the dependence on the critical temperature or the final size effect. The critical temperature computed and the chemical potential.
What is the
Final size effect.
we have not, there are theoretical publications which include the eigenvolume, the excluded volume of the newly emerging hadronic state into this statistical phase space consideration, excluded volume studies. Is that what you are asking for? But if you have, the answer is the following. If you assume a standard size of the hadrons, then the statement is not changing at all. If you try to introduce different effective radii for pions, kaons, etc., you are immediately a priori certain that you can get completely different results. No? Because now you have 6 new parameters, and all of a sudden the simple theory, which needs only 2 parameters, breaks down, and you have 6 additionals, and you can fit an elephant with this. No, let me be a bit more serious. At the moment when the hadrons are born, whether you are supposed to use the concept of their asymptotically ready formed radii is a completely open question. And the investigation of Johanna Stachel has just been centrally addressing the question what primordial hadrons really look like. Namely, they seem to somehow change their QCD wave function pattern. And so I'm not sure that one would really be on one's right path to really use excluded volume terms in this statistical analysis. But there's a long story to say. Hagedorn already worried about this for quite a while.
Yes, Peter.
Maybe just to that point, if one actually uses what is known in 20 years of nuclear physics as the hardcore radius of baryons, then in fact the effect of finite size of hadrons is relatively small and will not disturb the result of the analysis. And I think anything else is anyway inconsistent, because whether two mesons like to sit on top of each other or not is not something you can easily decide. So whether you then make a correction for mesons differently from baryons becomes completely uncertain.
Yeah.
And I think the only consistent way is to use the hardcore radius, and then the corrections are relatively small, the order of 50%.
Thank you. If there's no more question, I will ask Emanuele Kwerschik. to take the floor and take the mic at the same time. Emanuele will speak on strange signals of a new state of matter from nuclear collisions at CERN.
Thank you. Thank you, Reinhard. First of all, thank you, Reinhard, for having mentioned Hagedorn in this occasion, and I think was due. Then, coming to my talk, I have two small changes to the title. First of all, is strange baryon signals, and the second, I am also INFN Padova now, okay? I shall talk on behalf of the W97 and NA57 collaboration, and my talk will go through quickly motivation, experiment, results, and conclusion. Now, let me first start quoting the laboratories. Since there are two experiments, there is a large overlap between them, but there are some laboratories who are only in one, and they should be mentioned. Physics motivation starts from a suggestion of 20 years ago that if a QGP state is formed, one expects that the strange quark go in equilibration in a few Fermi over C, and this would lead to an enhancement of S quark versus UD with respect to normal hadronic interaction. The basic mechanism have already been mentioned by Uli: gluon abundance, partial restoration of chiral symmetry, and Pauli blocking of UAD quark, which at SPS energy is especially. Another consequence of this scenario is that hyperon abundances would be frozen at the critical temperature, since the hadronic reactions are too slow to compete with the rapid expansion of the fireball. This suggestion leads to two quantitative predictions. One is that in the final state, strange and anti-strange baryon and antibaryon will come close to hadronic thermal and chemical equilibrium. And this would lead to enhanced formation of strange and multi-strange baryons and antibaryons. The second is that in the hyperon transverse momentum spectra, one expects to see expansion flow effects of this expansion of the fireball. Now, all this has been already said. Why we concentrate, we spend a lot of time to extract the multiple strange baryons, that's the Xi and omega. Since their study is crucial because in the QGP scenario, like in any statistical hadronization scenario, their enhancement is expected to increase with its strangeness content. This is, therefore, in this scenario, one would expect that omega more enhanced than Xi, more enhanced than lambda, with respect to normal hadronic interaction. And such a pattern contradicts the expectation from rescattering in the hadronic fireball, since multi-strange particle formation is hindered by high threshold and low cross-section. Let me be more specific. If there is no quark-gluon plasma, you have a fireball full of hadrons which rescatter violently. Would be easy to form lambda and kaons, but much more difficult to produce multi-strange baryons, and especially antibaryons. If we make the example of the omega, anti-omega, for instance, either we produce it by direct interaction, and then you have a threshold of 3 GeV, or you have to go through a series of interactions. You produce once an antinucleon, and then a kaon, and so and so and so. And in the end, you will have an anti-omega, but that will take long time. So, the calculation depends, but is of the order of 100 Fermi for multi-strange antibaryon. So longer than the whole time involved in the process. So we come to the W97 NA57 experiment. You can find the information on the web. We made a special effort to update our page. So W97 looks for collision lead-lead proton lead and proton beryllium at 158 GeV per nucleon, beam momentum. And we study the production of lambda, Xi, and omega baryons and antibaryons. It has baryons which carry 1, 2, 3 units of strangeness. And we also look for K0 short and positive and negative particles. Negative particles are more interesting since they are mainly pions. There are no protons inside, no antiprotons, very few antiprotons. But anyhow, we concentrate on this lambda, Xi, omega. In a phase space window, which is spans about 1 unit around the center of mass rapidity, and PT larger than few hundred MeV over C. The centrality of the collision range, measured by the number of wounded nucleons, this means the nucleon that interact at least once, the number, which can be called the number of participants, between 100 and 416. 100 would correspond to an impact parameter of about 8 Fermi. So this is WA97. NA57 is its follow-up, is in progress, has the same aim as W97, but on a larger centrality range in order to see if there are centrality effect, thresholds or something, and also has been already taking data with different beam energies, and we are very eager to look at their results. So I will talk about W97. The setup was in the late omega magnet. This is the beam, a target, some multiplicity counters that we use to extract the number of wounded nucleons via Glauber model. And the heart of our detector is this 5 × 5 centimeter cross-section silicon telescope, which, however, contains 500,000 channels. And the whole thing, of course, is embedded in the omega magnetic field, 1.8 Tesla, and here we have some lever arm chamber to improve the precision on fast tracks. Now, to have an idea of the quality of this pixel detector, 5 × 5 centimeter, because we switched off the magnetic field, otherwise nobody could recognize any track. And then you can see 150T track reconstructed in a 5 × 5 detector. So where am I left? Good. So at that point, we concentrate on this decay, the decay of Xi in lambda pi, and decay of omega in lambda k, and the lambda in proton pi minus. These are the signal of Xi and omega we see. Here you have the lambda pi mass, where you expect here the Xi signal, and on this axis you have the lambda k mass, where here you expect the omega signal. So they are clearly there. This allows us to eliminate and correct for the region where omega and Xi are ambiguous, and therefore to extract the following very clean Xi and omega signal. Notice that the horizontal bin is 2 MeV. Now, once that we have this signal, what we do? Well, we do in the central unit of rapidity always, we plot the mass spectra and we determine the inverse slope of the transverse mass distribution. And then we determine also the particle yields and the collision centrality, so the number of wounded nucleons. In proton beryllium and proton lead are calculated via Glauber model. In lead, we divide our multiplicity in charge multiplicity in 4 classes, and via a wounded nucleon model fit, we determine the average values of participants in each one of these classes. We shall use that later. So the hyperon transverse mass spectra, here are the anti-omega, omega, Xi, anti-Xi, Xi. They fit the exponential distribution I just showed. And therefore, we determine the inverse slope. And what we do with this inverse slope? Well, we put on the same plot where there are the inverse slopes of other experiments, mainly NA44, NA49. The blue points are the inverse slopes of our K, lambda, anti-lambda, and psi, anti-psi. And here we have omega, anti-omega put together, but the slopes, the numerical value of the slope are very, very similar. This allows us to put them together. So what one can see is, one sees a general linear increase with the mass, as the Tully has mentioned, as a result of blue shift. And we see here something different for omega, which we almost immediately interpreted as an early freeze out of the omega. After all, omega does not have, the omega minus does not have elastic resonance with pi. Omega pi cannot form a resonance because the isotopic spin would be 1, and the omega is isotopic spin 0. Therefore, there are no resonance omega pi. Of course, could have resonances with other things, but more rare. Therefore, the cross-section is smaller, and the drag coefficient, consequently, will be smaller. This is very qualitative. There has been quite a microscopic, detailed microscopic transport calculation by Van Ecke, Zorg, and Su, who have predicted, these are their predictions, they even put a theoretical error on the omega slope. If I take their prediction and I superimpose to the slopes measured, you see the agreement is too good. Now, however, the point I want to make here is that the transverse spectra of these hyperons are described quantitatively by microscopic transport model. So the thing is in hand. The transverse spectra are in hand. So we are happy with that. Then, having done that, we move to yields, so number of particles per event. And we divide our particle into groups. Group of particles which don't have any quark in common with the target projectile nucleons, and particles which have some. We have some doubts about the K0, but we put it that because there were doubts. The reason why is that is empirically is known, saying then in proton beryllium, proton lead, there are differences between the rapidity distribution. Okay. So this is on the vertical axis. On the horizontal axis, we put the number of participants determined, as I mentioned before. So here is proton beryllium, proton lead, and lead-lead divided in 4 centrality classes, as I have said before. Now, that's fine. Of course, this has been corrected by acceptance efficiency. We have done a lot of checks. We have found that we get the table value for the omega lifetime, for the psi lifetime. So there has been, as usual, as all of us, a lot behind. There is a lot of experimental work which today is not mentioned. So at this point, we had 2 questions. The first question was, are these hyperon yields in lead-lead consistent with thermal and chemical equilibrium? The second question was, how does behave how is the pattern of hyperon enhancement when I go from proton beryllium to proton lead? So the first question, let's take the first question. You have already seen this transparency. You see, is a thermal model fit? Comparison between thermal model and experimental particle ratios done by these physicists, Braun-Munzinger, Reppe, Stachel. And the lines here, you see, are the model prediction, and the point are the experimental value with errors, and when there are no errors, they are too small. In blue, I circled the ratios where our experiment has, which come from our experiment. Here there is also a ratio coming from another, there are two, okay? The conclusion, our conclusion, my conclusion, and also, which is also the conclusion of the authors, is that the thermal and chemical equilibrium are closely approached in the fireball at hadrochemical freeze-out in lead-lead collisions. So the answer to the first question is positive. So let's go and look at the enhancements. So the enhancements, I mean, to see the enhancement, we put to 1 the proton beryllium yields for all kind of particles. Okay, so we have moved to 1 just to see the, we want to see the enhancement, therefore we have to choose a pivot. So we take there. If the yields were increasing according to the number of participants, they would follow this line, okay? Here also, I must repeat, is kept the separation between the particles which don't have quark in common and particles which have quark in common with the incoming nucleons. So as you can see here, the negatives are slightly enhanced, the lambda are more, and the xi are even more. The same is here in this group of particles. The anti-lambdas are little enhanced, the anti-xi are more, and the omega even more. Another way of seeing it is to do the yield per participant. Divide this by the horizontal thing, which is equivalent. And here it is. As you can see, proton beryllium and proton lead are consistent. And the enhancement are more or less equal in our centrality range. This means impact parameter smaller than something like 8 Fermi. Now, since they are similar, I am allowed to take average values. So I take average values and then I plot the enhancements. And this is the enhancement. For negatives, near to 1, the lambda, near to 2, and the xi higher, near to whatever, 7, 6. And for this particle, which have nothing to do with no quark in common with, you have the anti-lambda, anti-xi, anti-omega. Omega, anti-omega here are together. You may wonder why, what happened to the anti-omega. Okay, the statistics of course decreases, but here are the omega and the anti-omega separately. So we clearly see a hierarchy of enhancement. Good. So at this moment, I think I am ready to go to the conclusions. Conclusions concern hyperon transverse mass spectra. They agree with the expectation, with what expected from the thermal plus flow character. And we show the effect of early decoupling of omega in agreement with microscopic calculation. We are proud of this since, in a sense, we discovered this thing, which after all is very plausible. Hyperon yields, we confirm quantitatively the chemical equilibrium in all measured strange baryon and antibaryon abundances, which was a QCB prediction. We find that the enhancement going from proton beryllium to lead increases with the strangeness of the particle, and for the omega is the relatively large number of 15. Now, we want to stress that for multi-strange baryon, no hadronic microscopic model has predicted a strangeness enhancement leading to chemical equilibration. Now, addition of ad hoc new effects, we have looked several of them, made somewhere the thing better for the xi, but none of them has been successful in reproducing the omega enhancement. However, one criticism against this new ad hoc effect is called the Occam razor. Anyhow, now I have still a final conclusion, which is the following: that our pieces of the QGP jigsaw fit. Okay.
Thank you. Thank you, Emmanuel, for your talk, turning strange signals into a clear signal. And questions are welcome.
So, a simple-minded interpretation is that more nucleons are involved, so more strange quarks are there. So, if there are more, they favor to produce states with a lot of strange quarks, like Omega minus. So, it seems naively from data one could understand it way.
I think I answered first already that this cannot come from a rescattering in the fireball. Okay? Now, the other thing, I think Uli already answered you, is the time scale. If you have to do it very fast, the QGP way is, I remember already in the old days a talk by Van Hove saying that in the QGP, that kind of thing is fast. In a hadronic scenario, is going to be slow. That's the answer. Is that?
Yeah. Also, maybe you missed it, but the enhancement is per participating nuclei. So it scales more strongly than the number of participating by a factor 15 in the case of the omega.
Other questions or comments? I don't see any, so we'll go into the last talk. The summary by the DG, Luciano, please.
It's good. Non ti dimenticano. Comunque adesso usa hardware del CERN.
So that's going to be a very short summary, but let me start it by saying that I consider really a privilege to have been able to listen to such a clear presentation of results which have been accumulating during these years. And indeed, it's a very exciting summary of a very successful program. It was believed since many years that at very high temperatures and density, nuclear matter would undergo a phase transition. And let me show you my understanding of that with a very simple example. That's a familiar mountain for us at CERN. If the situation is like that, and you have a pair of skis, what's going on? Certainly a skier will be confined inside a patch like that. The situation improves if more snow comes, and there is a clear phase transition, which in many cases is called percolation or something like that. You now have long-range paths which can join points which are really distant from each other. And also there is another effect that what you could clearly define here as the inside space of a hadron now becomes confused because in fact there is more inside than outside. And that's exactly the reason of the phase transition. Of course, this is now well established quark gluon plasma when a skier can go up and down and roam freely. Unfortunately, the example is not perfect because in the real world, temperature goes up that way, but in this case, you will notice that in the analogy, temperature should go the other way around. Coming to a more serious point, I would like to stress the international nature of this program. When this program was decided, CERN had not much money to spend on it, and it was made possible by the collaboration of many laboratories, which are listed here, to construct the facility. I think this is an important point to stress. Of course, the international participation in the experiments is much wider, but that has been given space this morning, so I think it's useful to keep in mind that. As I said, I don't want to make a summary because I would be repeating what you heard just today, but yesterday, with the help of John Ellis, we tried to summarize what is the picture that comes out, and in fact, it's very exciting. It's really a small Big Bang. Again, now temperature goes in this way. What we learn is that in these collisions, there is a sort of last scattering surface, the place where really hadrons freeze out, and that is expanding at a remarkable velocity. It's half the velocity of light, and from various combinations of interferometry, energy, etc., we can fix the temperature, a rather low temperature on our scale. It's under 20 MeV. More inside, at about a temperature of under 70 MeV, we have seen this very interesting and clear signal of the formation of strange particles. We hope out of an equilibrium where strange quarks were more abundant than normally. And even more inside, the remarkable signature of the melting of the J psi, perhaps with a clear, or maybe not so clear, but certainly tantalizing indication of different regimes where at high temperatures, where the psi prime melts before, that is at longer distances, that is at higher temperatures, that there is an intermediate melting of the intermediate states, and then finally the very closely bound state, J psi, is melting. What we still do not see is a clear picture of the photons, which are still confused, and that maybe has to do with the fact that its volume is not yet sufficient to see all that. But I think that the very fact that we can try to form this picture like that signal what Ulrich Heinz has called a quantum jump in our understanding of nuclear matter. In fact, that's the most impressive result of today's discussion when you put everything together. Although some bit and piece can be explained in alternative ways, my feeling is that, in fact, we are seeing a new picture. That's going to be only the beginning of the story, fortunately. We have many other things to see, many other things to do, so I will conclude my summary just by giving you a hint of the next steps. Well, that's the beginning. That's where the action is going to be next. Long Island, RIG collider, which from this summer we start taking data, but then, don't forget, 5 years from now, we'll be back at CERN with the Large Hadron Collider, where from the first day, heavy ions will be colliding. And I hope that by this further means we will be able to not only pin down all the details, but also really make a new understanding of nuclear matter at high temperature. Thank you very much.
So this concludes this special scientific seminar. I think we can thank all the other speakers this morning for a consistent, broad presentation of all what has been accomplished and all the results obtained, which provide a very consistent picture indeed. Thank you very much.